Myself, Shivakumar, research scholar, SRM University, AB. I have done a research on cryptography, that is a strategic framework which implement post-quantum cryptography using quantum key distribution technique using in a 16 network. According to NIST IPS, so secure communication over a 60 has to be done. So my model here, a hybrid model related to which classical cryptography like RSA can be become vulnerable by cryptography, quantum cryptography. So for this solution, I have proposed a post-quantum cryptography technique. I'll show you the visualization way. So these are the challenges that are being facing while implementing the 60 network. That is, while transmitting the data in terms of packets, the latency getting dropped. Okay. So to secure the communication in a 60 network, we have to introduce a post-quantum cryptography keys, which will increase the latency. So to solve this problem, so we have proposed a hybrid framework, and the second thread for the 60 network is HNDL, that is harvest now and decrypt later. Means, so we are into the area of cryptography and quantum cryptography. So what is happening is the hackers are collecting the data, and then later they want to decrypt later using the quantum techniques. So how the modular cryptography architecture for 60 is this? So basically, I have explained in 3 tiers. The first one is Sauvignon black hole, which represents the communication between a client and server, or from one party to other party, how it is done with an hardware integrated KQ2 module is being done. And the second tier, it's related to the both hardware and the software integration, how data is being transferred. And later the third tier, so this is about resource transferring device wireless flexibility. So implementing a lightweight post-quantum cryptography technique. So I'll explain in detail the 3 tiers. So this is the first tier. So while data is being transferred, basically for the faster communication we use fiber optic cables. So if a eavesdropping is being done, an intrusion alert will be happening. So for to detect this, basically we have proposed a mechanism to implement. So basically this is what happens in a image as you see here. A single polarized photon is being there, and a mechanism is being defined where quantum key distribution protocol is being implemented, and thus a continuous laser beam of phase has been happening with a secure key communication. And so later on with this, the protection can be done in a data center along a minimum of 10 years. So this is the type 1 which implements the quantum key distribution layer. The second one is about implementation logic I have done. That is the second one, that is hybrid post-quantum cryptography. Right? So this is implementing the classical way of integration and both hybrid and post-quantum cryptography modules together. And what I have done is implemented using a VPN, virtual private tunneling concept. So with this, a secure communication can be done using a 60 network. And with this, high-speed data flow can be done, and additional no quantum hardware is not required for every node. And this is the third tier which I used, which is using of a lightweight post-quantum cryptography. So by using a lightweight cryptography key like stream ciphers, or you can say salsa, cha-cha. So these are the lightweight stream ciphers that can be used. So by using these lightweight stream ciphers, which consumes less power, right, and less RAM and not much heavy quantum math is required. So 6G devices in a smart cities which require no battery drain, and these are quantum safe, and no network lag will be there. So this is the simulation which I have done. I will introduce these three tiers using Python programming language, where a 6G infrastructure with 10 Gbps Blackwell. That means that I will introduce a simulation which gives me the results that depending upon the throughput, handshake, and packet dropping and CPU load. So I have verified with the previous ongoing procedure and implemented with the 6G network. So while comparison with the post-quantum cryptography and the hybrid one, so the data transmission in a secure way is going very faster. So I have developed a simulation where with the post-quantum cryptography and implementing the hybrid framework. So these are the results which I got. So faster communication connection has been established. So the handshake latency means the time taken to connect from a client and server, and so which has been reduced to 42%, and which takes 22 milliseconds when I implement this hardware hybrid model. And the packet drop rate means while transmitting the data from one node to another, so there is a significant packet loss with the previous model. So in this model, it is being around 0.20% of packet drop rate has been done. And then coming to CPU load, so while implementing this concept of 6G, right? So standalone post-quantum cryptography takes approximately around 19%. When I implement this in a hybrid module, it takes around 7% of the CPU load. So the faster communication can be done. And so the reliability is like 99.9%. See, by implementing my hybrid model, through Python implementation, simulation has been done. So secure communication can be done. So how the roadmap can be done on implementing the 6G. The first one is data crypto period assessment. So for taking care of implementation of hardware. This is not an implementation of hardware. So what I have done is integration of both software and as well as hardware. Like so the hot swappable cryptography. So replacing the hardware along with the implementation of the software together. So the next thing is interoperability and standards. So whoever the vendors may be, providing a proper gateway and providing a secure way communication can be done. So the path of quantum resilient, 6G generation. As I summarized, actually told you, the architectural module is a key. So swapping of hardware with an implementing of the cryptography, lightweight stream ciphers. Okay. So the hybrid model gives me successful results. And this is as I proposed the three-tier architecture: type 1 with a quantum key distribution, type 2 with a hybrid post-quantum cryptography, and type 3 with lightweight post-quantum cryptography. So finally, so the 6G network secured against HNDL. Harvest now, decrypt later. Thank you so much.
A rare disease combination. You give long tokens, acceptable overhead. So expected number of tokens is P of dy times L of dy, minimized with probabilistic hierarchy. Application domains like medical diagnosis, agricultural advisory, maritime inspection. The challenge is rural healthcare, limited connectivity, mobile health advisor with diagnostic pathways, benefits 100 to 500 milliseconds response time. In agriculture, seasonal decision, resource poor farmers, solution crops, pests, soil knowledge, encoded hierarchy. Maritime inspection, underwater robots, GPS denied environment. So vessel, suppose you want to go to a ship and you want to make sure the ship is in a proper condition. Vessel integrity assessment procedures, autonomous decision making, no cloud dependence. So, resource optimization techniques. Quantization, one of the ideas, model compression. 32-bit to 48-bit, 4-bit and 2-bit precision. Pruning. Remove non-essential parameters. Results 40 to 60% parameter reduction. Then we have knowledge distillation. Large teacher to small student. Benefit retail, task knowledge discard generality. Token allocation optimization is based upon a greedy algorithm. So you know, when you want to compute minimum spanning tree, you use greedy algorithm. So greedy algorithm assigns shorter sequence to high probability items, longer sequence to rare items. Now, performance metrics trade-offs, cloud-based LLM versus domain-specific, model size 7 billion parameters to 2.8 to 4.2 billion parameters, 40 to 60% compression. Inference latency 2 to 10 seconds through cloud to 100 to 500 milliseconds, local 10 to 50% improvement. Energy consumption, high to extended battery life. Trade-off, semantic flexibility versus predictability. Domain-specific systems sacrifice generality but gain. With gain efficiency, validation and regulatory compliance. So the implementation challenges are labor-intensive collaboration with domain experts to design optimal hierarchies. Model maintenance, periodic updates as domain evolves, incremental learning for edge devices. Safety and validation, rigorous testing of bounded output space, regulatory compliance per domain. Connectivity issues, graceful degradation when updates cannot be downloaded. The advantage is bounded output space makes validation systematic, auditable compared to general purpose LLMs. So, how source coding achieves the goals? Efficient token allocation based on the probabilities, probabilistic hierarchies, minimize average token consumption, reduce latency, local on-device inference eliminates network round trips, energy efficiency, smaller models consume less power, domain optimization, structured knowledge exports domain-specific patterns, predictable outputs, menu-driven interface ensures all right. Conclusion, source coding theory provides a rigorous framework for deploying LLMs on resource-constrained devices. Efficient compression, low latency, energy efficient and validated output. Three proven applications are medical diagnosis, agricultural advisory, maritime inspection. The intersection of information theory, domain-specific engineering, and neural network optimization enables AI everywhere. Future directions, automated knowledge graph extraction. Can ML techniques automatically generate optimal domain hierarchies from unstructured knowledge. Federated learning enable collaborative improvement across institutions without centralizing data. Multiple hospitals, architectural innovation, mixture of experts with domain-specific sparsity patterns, cross-domain segment, generalizing principles for designing hierarchies in novel domains. So this essentially was motivated by the fact that in source coding you do data compression. When you zip a file, you are doing source coding or equivalent data compression. So our main idea was to apply source coding theory to domain-specific LLMs. Any questions? The whole paper is available. It will be printed.